In this lesson, we're going to look at some more of the tools and basic building blocks of calculus. In particular, we're going to look at rationalizing and rates of change. So, rationalizing is something we learned about in grade 11. We learned about radicals and how to break them down. So, just some quick reminders. When we have a non-perfect root, for instance, root 8, we often want to break it into its perfect part and its non-perfect part to make a simpler version of the same radical. So for instance, I could break root 8 into root 4 and root 2. One of our rules was that if you have a root times another root, it's equal to the root of those two things multiplied together. Okay. Root 8 breaks into root 4, root 2, which we can simply write as 2 root 2. This is a simpler version of that. Okay, so root 27, the perfect root would be root 9, the non-perfect would be root 3, or in other words, 3 root 3. If you have a number in front, a coefficient, okay, so for instance 2ab, we could break that into 2 times root a times root b. So if we get something like that, we can keep the coefficient out front, the perfect root, the non-perfect root. Whenever you write things all written together like this means multiplying, right? These two things. So if I break root 25 into root 20, sorry, root 15 into root 25 root 2, we can think of that as 2 times 5 root 2, which is 10 root 2, a special, simpler version of 2 root 50. Roots can also be added like algebra. So if we had 2x plus 3x, we can make 5x. But they have to have like terms. Well, in our case, it means they have to have like radicals. So 4 root 2 plus root 32 doesn't work. But if I break root 32 into root 16 and root 2, we get 4 root 2 plus 4 root 2, which makes 8 root 2. And that might be a simpler version because of obviously only got one part compared to the two initial ones to start with. So some just basic reminders about radicals from last year. If you can, try and make the perfect root first. Remember, perfect roots are ones that come out to whole numbers. Radical functions are often really challenging to work with, in particular when we're trying to find our rate of change. You dealt with that last year in higher functions. So to make this process a little bit simpler, we like to rationalize things. That is, we like to remove the radical from the bottom of the fraction. This can be done by multiplying the entire fraction, top and bottom, by the radical you want to get rid of. It's okay to have radicals on the top. We just try to avoid them in the bottom, in the denominator. So for instance, if I had 5 root 2 and I want to get rid of the root 2 from the bottom, I can multiply the whole thing by root 2, top and bottom. If I do that, I get 5 root 2 on top. They're not radicals, so the whole number goes in front, the radical goes afterwards, over root 2 times root 2 is root 4, but we know root 4 is just 2. So even though it looks sort of more complicated, this is a more forgiving way to work with things, having the radical on the top. Yeah, we do the same thing in B. Our objective here is we want to get rid of the root 3 from the bottom. The 2 is okay, it's just the root 3 that's the problem. So multiply the whole thing by root 3. If we do that, we're going to have to multiply this by root 3, which equals 4 root 6, and this by root 3, which is 3 root 9, all over 2 root 9. Now the nice thing is the root 9s we know we can break down, so 4 root 6 plus 3, remember it's multiplying, so 3 times 3, and 2 times 3. So we get 4 root 6 plus 9 all over 6, and that's about as far as you can go with that, because there's no common factor on the top, nothing you divide 4 and 9 by, you can't simplify it anymore. And if we try the last one, I want to get rid of the root 2, so root 2 and root 2. I'll end up with 1 times root 2 is just root 2, root 5 times root 2 is root 10, and root 2 times root 2 is root 4, or in other words, just 2. And we can skip the step of having to write out the root part, because we know two roots multiplied by each other just creates the number itself. Okay, so some basic rationalizing. Sometimes you have more than one radical in the bottom, in the denominator. If you do that, have that situation, we need to get rid of both of them. And the way we can do that is by multiplying by the conjugate. The conjugate, new word here, has the same radical terms, so same root signs, but has opposite signs between them. The idea of like a difference of squares, if you will. And when we multiply, we're going to have to do some FOIL here. So for instance, the first one, I want to get rid of the root 3 and the root 5. So I'm going to multiply by root 3 and root 5. And I'm going to do the same thing I did before, so top and bottom. In the question, there was a plus sign. So in my rationalizing, I put the opposite sign, minus sign in both. So now when I multiply, I'm thinking about FOIL here. I'm going to multiply this and this and this one and this one. And do the same thing for the bottom. So we'll end up with 2, and root 3 times root 3 is just 3, minus 2 root 15, minus a root 15, and then minus times a minus is a plus, and root 5 times root 5 is just 5. On the bottom, root 3 times root 3 is just 3. Root 3 times root 5, well, it's negative root 15. When I do the inside ones, I get positive root 15. And then when I do the last thing, root 5 times root 5 makes negative root 25, or just 5. So up top, I end up with a 6. I have 2 root 15s in the middle. I can collect them. So 3 root 15 plus 5. On the bottom, I end up with a 3. If you do this right, these two things obviously will cancel each other out. And then minus 5. On the top, I can simplify a little bit further. I get 11 minus 3 root 15 all over negative 2. And I've taken something, I had 2 radicals in the bottom. I've gotten rid of both of them. Yeah, I can do the same thing in the next piece. Multiply by the conjugate. I've got multiple parts. It tells me to do the conjugate. Conjugate is same radicals, opposite signs. And then FOIL. So we can get 2 root 25, or 2 times 5. And we're doing FOIL, right? So we did that one. Then we'll do this one, which is just a root 5. We'll do this one, which is a 2 root 10. And we'll get this one, which is a root 2. All over 2 root 5 times 2 root 5 makes 4 root 25, or in other words, 4 times 5, plus 2 root 5, minus 2 root 5. And 1 times 1 is 1. Simplified, we'll get 10 plus root 5 plus 2 root 10 plus root 2 all over. These two will cancel. So we'll get 20 minus 1, in other words, just 19. And yes, it definitely looks more complicated, but it will be easier for us to deal with algebraically, calculus-wise, to figure out that ROC equation if we don't have radicals on the bottom. That was our objective here. Okay, when dealing with rate of change, so we're going to that ROC idea now. We want to rationalize the numerator sometimes. Okay, depending on where the situation is, are we dealing with a rational expression which has a radical on the bottom, or do we have a radical on the top? It's often easier to work with the alternate version. So if we look at an example of how we can use this idea of rationalizing when we want to look for an ROC in a radical expression, we can go back to what we learned about yesterday. So we said our ROC can be found, or our slope gradient, I mean the same thing, is the limit as x, sorry, not x, h, the limit as h approaches 0 for our function. So our function is wherever I see an x, I'm going to place it with an x plus h plus 2 minus the function all over h. Now, if at this point I tried canceling, it wouldn't really work because I have all 3 of these underneath the radical sign. Can't really do much with that. If I put 0 in for h, I get the same thing left side and right side on the top, so it wouldn't simplify anything. I get 0 over 0, which would cause a bit of a problem. So this is a situation where rationalizing can come in handy. And I'm going to rationalize, oops, don't hit arrow there, or line there, sorry. I'm going to rationalize the top. Okay? Sometimes when I have the radical on the bottom, I'll rationalize the bottom. Sometimes when I have on the top, I'll have to rationalize the top, depending on what I want to get rid of. So I'm just going to get rid of the big brackets. I don't really need them. This is my top. And I'm going to rationalize this by multiplying by the exact same thing. There should be a root sign right here. By multiplying the exact same thing, but with the opposite sign in the middle. So right now there's a minus sign between the roots. So I'm going to put a plus sign in between the roots. On the bottom, exactly the same thing. And what's going to happen here when I rationalize? Well, a couple of cool things. First off, what happens when you multiply a root by itself? We said that what happens when you multiply a root by itself, for instance, root 2 times root 2, is you get root 4, or you just get 2. In other words, the radicals just cancel each other out. So when I multiply root x plus h plus 2, so this one times this one, the only thing that's going to happen is the radical part will disappear. So I'll get x plus h plus 2. Okay, and then when I multiply my middle terms, so this one times this, and this one times this, because they have opposite signs between them, they're going to cancel each other out. Kind of handy. So all I have left then, the part of the end, the FOIL part, is root x plus 2 times root x plus 2. Notice there's a minus sign in the middle. So I'm going to have a minus. And what happens to the root multiplied by itself? It just cancels it out. Now I had to put in brackets because of this minus sign right here. And that came from the FOIL idea. Okay. On the bottom, instead of actually multiplying, I'm going to write down an h times root x plus h plus 2 plus root x plus 2. Okay, so let's simplify a little bit. Limit h approaches 0. What can cancel? Well, I can cancel an x minus an x. A 2 minus a 2. What am I actually left with? Just an h. On the bottom, an h times x plus h plus 2 plus x plus 2. Well, what can I do with these h's? I got one on the top and one on the bottom. What can I do with that? I can cancel those out. So I can take this h and say that one's gone, that one's gone. On the top, I'm left with the number 1. On the bottom, I'm left with root x plus h plus 2 plus root x plus 2. And that's about as far as I can go in terms of simplifying. So what do I do now? I replace the h with 0 because I want to see what happens as I approach 0. Now I will get 1 over x plus 0 plus 2 plus x plus 2. Or in other words, 1 over root x plus 2 plus root x plus 2. Hey, it's the same thing twice, right? And they're being added, so it's reducing 1 over 2 root x plus 2. This is my function for IROC at any point on that curve. It said find IROC at 3, so at x equals 3, my IROC will be 1 over 2, 3 plus 2, which is 1 over 2 root 5. If I already want to take a punch in the calculator and figure out an actual value, not a big deal to do that. Just use your calculators. Okay, and that's how we can sort of use radicals in a much more challenging situation. As I said, sometimes you're going to want to radicalize the bottom, sometimes the top, depending on what the original function looks like. If the radical is in the bottom at the beginning, that's when you need to rationalize. If it's in the top of the beginning, that's when you need to rationalize. Okay, some more building blocks for calculus. So we're going to deal with word problems in this course, obviously, and how we can apply this information. The general idea of calculus is how does IROC work, the rate of change between two variables. But it doesn't always have to be just rate of change. I'm not going to say the words rate of change. Sometimes we're going to think about some realistic situations. So a common one, volume. Well, your volume can change. Let's say you had a can, if it can. How is the volume going to change? Well, the rate of change, pouring stuff into here, is, well, it depends on maybe how high that can is. The taller the can is, the slower the volume is going to change. Or maybe it's a really narrow can, right? It's really narrow. Well, then the height changes. So volume often depends on length, width, height, or radius. Okay, maybe length and width if you're talking about a prism, height and radius talking about cans, pyramids, things like that. Air temperature. It often changes. And you're climbing up a mountain, the higher you climb, in other words, your elevation, the more your air temperature changes. Okay, so that's a common situation. Areas are two-dimensional versions of volume. And the one we're going to spend the most time with, and the most common one, is the relationship between distance, speed, and time. So let's look at that last situation. So velocity. We talked about velocity when we did vectors, and velocity is a vector because it has a direction and a size. And the way velocity really works is over time, you change your position. So my position is changing with time, right? So we can say there is a change in position. And if we divide that by our change in time, we're going to figure out our velocity at that instant. So how far have I gone from there to there? How long did it take? Okay, if I want to figure out how fast I'm going at any moment in time, I can figure out the ROC at that single point. That would be our velocity relationship. Okay. Average velocity, just in general, AROC, the same way we've done before. IROC, that's our important one for today. IROC is the rate of change of your position at an exact moment in time. So generally, and these are the letters we use, position is given by st. So position displacement is s at a certain time t. Velocity, v at t, is the limit of that. It's the IROC of that. So you notice we have this notation here. And that's how we can find our velocity at any time t. We take the rate of change of the displacement. And there's some simple properties we're going to look at. And so if you have a negative velocity, that means your object is either falling, going downwards, or it's going backwards, right? Depending on if you're talking about up and down or left and right. If it's positive, the object's rising, moving forwards. And if your velocity happens to be 0, then your velocity, if your velocity happens to be 0, it means your object was stationary, or maybe it was changing direction. So maybe it was falling, and then it stopped, and then it started going back up again, if we think about their tangents. Okay, so some simple examples of how we can use these little ideas here. And these are just our basics. So displacement and velocity are related to each other. So the velocity of an object given by this equation, at what times is the object at rest? The object's at rest when my velocity equals 0. So if I take my equation and I make it equal 0, and reflect back on quadratics, or in this case cubics, we know things equal 0 when each piece equals 0. So either ts equals 0 or t minus 4 equals 0. In other words, t equals 4. So there's 2 times where this object is at rest. Now it may be stationary, not moving, or it might be changing directions, but it's at rest. It's not moving at those 2 points. Okay, so we can approach these things the same way we did quadratics and cubics and quartics and all those other things. We just have to recognize as a language is talking about change in your rate. And last example. So we got an avalanche, the motion of it, described by this equation, where s is a distance traveled by the leading edge of snow after t seconds. Find the distance traveled from 0 to 5 seconds. So distance, that's using our basic equation. So at s0, we're at 0. S5, after 5 seconds, 3 times 5 squared is 75 meters. So it's traveled 75 meters in the first 5 seconds. Find the rate at which the avalanche is moving from 0 to 5. Well, movement is a rate of change. Because they're giving us 2 different values, we're looking for an AROC. So we're looking for S at 10 minus s at 5. Oh, sorry, s at 0. And we can find those two things. So 3 times 10 squared minus 0. We already know the displacement 0 at 0. We did that over here. Divided by 10. So we get 300 over 10. Or it's moving 30 meters per second in the first 10 seconds. Okay. Find the rate at which the avalanche moved in the first second. So the first second would be from 0 to 1. That's in first second. Because again, I have two different points in time, and I have AROC. So the first second would be S1 minus S0. So S at 1 would be 3 times 1 squared. We already know this is 0. This is going to be 1. So we're going to get 3 meters per second. The second part of that question asks what's happening in the fifth second. So the fifth second, AROC again, is from second 4 to second 5. So we need to find s at 5 minus s at 4 over 1, or 5 minus 4. Now, s at 5 we've already found out was 75. That would be right here. S at 4 we haven't done yet, so let's find s at 4 over 1. So we get 75 minus 48 over 1, or in other words, 27 meters per second. So as you can tell, it's picking up speed, right? It started at 3 meters per second in the first second. By the fifth, that's 27 meters a second. Okay, find the rate at which the avalanche is moving at 10 seconds. So the different words here, at 10 seconds, as opposed to in the first second, references IROC. So really part D wants to know IROC at x equals 10, or t equals 10, because we're talking about time. Okay, so to do that, we need to build that equation, right? That equation for IROC. So IROC equals the limit as h approaches 0 for the function 3t squared. So we need 3x plus h squared minus, actually it's t, sorry, do it again, minus 3t squared all over h. So limit h approaches 0, we're going to have 3 times t plus h twice, or in other words, t squared plus 2th plus h squared if you FOIL, minus 3t squared all over h gives us the limit as h approaches 0, 3t squared plus 6th plus 3h squared plus 3h squared minus 3t squared all over h. We know those 3t squared should cancel out. We're left with just the h parts, which we can common factor. So if we take out a 3 even, 3h, we'll be left with 2t plus h all over h. And we know the h's can cancel, so we'll be left with the limit of h approaches 0. Cancels these h's because they're multiplying now. 3 bracket 2t plus h. What happens when h approaches 0? We get 3 times 2t plus 0. In other words, just 3 times 2t, or 6t. Here's our IROC for any point in that graph. I want the IROC at time equals 3. So when time equals 10. So our speed, our velocity at 10 will be 6 times 10, or in other words, 60 meters per second. It's moving pretty quick at that point. Okay, that's how we do part D. Part E, how long do the intersections of the leading edge of the snow take to move 600 meters? 600 meters. Well, that's not a speed, that's a distance. So I'm going back to my original equation for letter E here and saying, okay, 600 meters, I want to know how long that took to happen. So this was our displacement, right? So that is 600 meters, so we can solve this. both sides by 3, and then we square root it, and t will come out to approximately 14.1 seconds. Okay, so some basics of how we can work with rational expressions and some ideas of building blocks about calculus in terms of displacement and velocity being related to each other. IROC for displacement is velocity.